Hello, good morning. I'm Milind here. Along with me, it's Pandurangan. We are from Arista Networks. Third year coming here. Wonderful to see the attendance this year. Amazing to see that 2 days we had to push it. Basically, it's too good. Thank you so much. We have been actually talking about the actual contribution to SONiC all the time. Last year we talked about modular systems in SONiC. Last year we talked about counters, specifically VOQ counters. This year we are going to go more into telemetry with specific focus actually on the frame loss ratio and other stuff that is very useful for the debugging. So outline, basically we'll talk about the L1 telemetry troubleshooting, basically forward error correction basics, some formula things. I'm going to talk a little more about theory and computations, whereas Pandurangan will talk about Arista's contribution to the same area. In terms of theory, the more the speed, the chances of the lines getting more and more error prone because of the distance, because of the dirty fiber, because of the bends, etc. in the line, the number of errors start going up actually. So it is very important aspect to catch up on these errors, figure out ahead of time that the link is going bad and take the corrective measures. One of the options that is already known actually, it's a standard one, FEC, the forward error correction, which helps you automatically do correction of some of the bits. That gets a standard technology that gets used. Checking that FEC statistics is more important from that L1 troubleshooting perspective. Continuous monitoring of it will give you actually the idea about how the link is going down or it is stable. Typical thing, you get basically data in, the encoder will encode the packet, add the parity to it, and the receiver can actually look at the parity, do some corrections, do some detections of the bits. That's a very typical scenario that we always see. That continues with this also. The important thing is the FEC code word basically. Every frame gets divided into multiple code words and then gets transmitted. This code word, they have got multiple things like, as you can see here, read Solomon code, which has got 544, as you see the number, first number, 544 here. That is the one basically. Those many symbols are there, out of which basically 514 symbols contain actual message and 30 symbols contain the parity side. So with 30 symbols, each symbol is basically 10 bits that you can use. And with 30 symbols of parity, you can correct 15 errors and you can detect 30 errors, right? That's the meaning of code word. Similar to 544 and 514, there is a technology 528 and 514. Instead of correcting 15 bits and detecting 30-bit errors, instead of that, you have now here correction of up to 7 symbols and 14 symbols for the detection basically. The important ratio, there are multiple ratios that are going to come into picture now. One is called as code word error ratio basically, which is nothing but number of correctable code words over total number of code words which are being transmitted. The more the number of uncorrectable code words start going up, obviously your link is starting to degrade. That's the meaning of it. It gives multiple buckets. This is the histogram basically. The bin 0 is nothing but number of code words which are transmitted without any error. Bin 1 is nothing but number of code words which are being transmitted with one error. 2 means 2 errors, 15 means 15 errors which are getting corrected basically. So these bins are given to you. The moment higher the bin number count starts going up, basically more and more bits are getting or symbols are getting corrected. That's an indication of basically the link degrading more and more. By standard ITU and MEF, these are the fundamental service level agreements. It is for the proactive detection of the issue and effective troubleshooting. They move the conversation from subjective to, it's more about quantitative data now instead of just talking about bad performance of the link. How do you quantify the data? The simple thing is it is FLR, the frame loss ratio. As I said, the frames are divided into code words and then the code words are sent across, correction happens and the code words are collected together, collated, and then actually frame gets formed. So the number of lost frames because of uncorrectable errors versus the number of total frames that are transmitted is a simple ratio of frame loss ratio basically. If this starts going beyond non-zero number, you are very clear, the link is starting to degrade basically. As I said, the frame gets divided into code words, and then the FEC FLR comes into picture, where frames that are uncorrectable by FEC. So FEC we talked about, you can correct 15 symbols, whereas you can detect 30 symbols. The moment it goes beyond that, you cannot correct it. So the number of uncorrectable frames by the FEC versus total number of frames transmitted is the ratio basically called as FEC FLR. In the normal operations, when the link is healthy, obviously FEC FLR is going to be 0. There are no errors happening. The symbols and the frames are going perfectly fine. During degradation phase, you will start actually seeing the correctable errors going up, as we saw bins from 0 to 15. Bin number 1, bin number 2 with 2 symbols, 3 symbols, 4 symbols that getting corrected. So it's degrading. You are still able to correct the frame, salvage everything. There is nothing else going wrong. But at the same time, it is clear that the link is degrading because the correctable errors are happening. And there comes a point where you reach a point where you cannot correct the code words. That is the overload point where errors exceed the FEC's correction capability. In this case, example we talked about. The 15 symbols can be corrected. If it goes beyond that, you cannot correct it. That is the point called as overload point. In Ethernet, frame size varies obviously from 64 byte to 1500 bytes, or even from jumbo frames, it's bigger than that. But you need to find the correlation between the FEC FLR, the FEC frame loss ratio, versus what is the frame size. So these are two formulas. We don't need to go into all the details of these mathematical equations. But by and large, the FEC FLR is nothing but basically the code error ratio, code word error ratio multiplied by 1 plus MAC frame size divided by code word size. That actually translates into the lower formula that is shown here, which is nothing but code word error ratio multiplied by 1 plus 1 by MFC, right? Problem, so this is all great, but then how do you actually go and implement it? So the majority of the problems start coming up when the burst of traffic starts, burst of noise or interference corrupts actually the symbols or the code words. That's where the problem starts. This can overwhelm the correction capability of a single fake code word. The entire code word may get lost, right? So now what happens, you are taking the frame, dividing into multiple code words, and code words are being transmitted. If a code word gets lost, you are starting to get into trouble because of bursty or noise or because of the interference that happens. So instead of sending code words, so once you divide the frame into code words, you will get the topmost line, basically the 1, 2, 3, 4, 5, 6, 7, and up to 16, for example. These are the code words. Those are there because of the frame that is divided into it. But if you interleave the code words, the chances of recovery are better. If you transmit 1, 2, 3, 4 as 1, 2, 3, 4, 5, 6, 7, 8 as 5, 6, 7, 8, and so on, and suppose 9, 10, 11, 12 gets lost, then basically there are 4 code words here. The capability of recovering that is much lesser because you are losing the entire code word. But if you interleave one code word from batch of 4, so you collect together 1, 5, 9, 13 in one batch, then 2, 6, 10, 14 in the other batch, 3, 7, 11, 15 in the other batch. If you do that, and suppose this code word gets lost, right? Now, because it is distributed across, this code word was 3, 7, 11, 15, it gets lost, and it was supposed to be recovering 1, 2, 3, 4, 5, 6, 7, 8. It is only one code word that is getting lost in a batch of 4. So the interleaving is very, very important. Even if you lose the code word, basically the recovery is going to happen. If you do not interleave, the recovery cannot be done. So this is one method of how do you interleave the code words so that the recovery happens better. And then corresponding interleave factor and corresponding ratios are there, which will help you calculate the FSF, something called as FLR scaling factor, which takes into account the interleave factor. In the example that we saw right now, this was 4 code words getting together. You can have 8 code words coming together, 16 code words being interleaved together. That interleave factor can be taken into account depending upon what type of link it is. It is 800 gig or 400 gig or 100 gig, depending upon that. The table is there later on also. Right? So basically, this is the information that it talks about. For example, for 1600 gig, you can have 8 lanes and you can do basically 4-way interleaving. For 400 gig, you can do 2-way interleaving. That is what the interleaving factor we just now talked about. It's all about making sure that as much as possible, the errors are corrected as much as possible so that we don't lose the frames. I mean, what yesterday he talked about in Broadcom, all that whole retransmission, etc. That's much more advanced compared to that. There is no retransmission, of course, but we need to have some capability of correcting the corresponding code word so that the recovery of the frame happens better, right? So that's the theory behind entire frame loss ratio and corresponding all the mathematical formula. Pandurangan will talk more about basically how is this being implemented in SONiC so that the telemetry, which is one of the basic and most important factor of any networking device where the monitoring capabilities are going to be looked at very closely. He's going to talk about the telemetry, right? Over to you.
Thanks, Milind. Thanks for covering the background on FEC and FEC FLR. Now we will see about, with all the data that we have, we'll see about what it takes to implement FEC FLR on SONiC. So today we already have support for FEC histogram in SONiC, so which displays the data this format. So already Milind covered it in the slides. So basically just to see there are corresponding SOI attributes already, starting with like underscore S0 for 0 symbol errors, S1, and all the way up to 15, which is the max number of correctable symbols per code word. So we have the data already exposed in SONiC. So one part is already there. So coming to the next part, we also have the FEC uncorrectable frames, like which is actually the code word. So that is also there. So basically all the core statistics that we need for computing FEC FLR is available in SONiC. So it's a matter of implementing the layers on top of it to compute the FEC FLR and provide it to the CLI and telemetry. So that's what the further talk will cover about. So now we are going to look a bit into the changes that is needed in Redis DB. So this is the FEC FLR itself, which we are going to compute. So that of course will be stored in Redis DB in the rates table. And then we also store the port statistics, the FEC statistics for the last time period FEC FLR was computed. So this is needed because we are computing FEC FLR over a time period. So we'll probably see that in the next slide. So these are the two major changes that is needed from the DB side. Every 120 seconds, we compute the CER. So that's the interval over which the FEC FLR is being computed in SONiC as of now. So, and the data will be kind of read from the counters DB and stored in the counters DB. So how do we compute? So it's basically the delta of uncorrectable errors over the time period by the delta of all the code words in the time period. So that's the CER. So we already covered it, just the implementation part. And then we kind of compute the FEC FLR based on this, and every time, right, we compute, we of course update the last values in the counter DB so that we can start computing from the new time period again. So that's what happens. So already we have the portstat command, which corresponds to the CLI, show interfaces, counters, FEC statistics. So now we have enhanced to support the FEC FLR column. So it kind of shows the FEC FLR which is stored from Arc agent side. So it is it's populated to DB, and the same thing we are just displaying here now. So we have FEC FLR and everything. So one kind of significant drawback of just looking at FEC FLR is when we see a non-zero FEC FLR, it means that the link has already gone bad. It's just a measure of how bad it is. So that helps in one way, but that's probably not what we should be looking at all the time though. So we have come up with a proactive approach of doing the predicted FEC FLR computation. So it tries to analyze the data from the FEC histogram and computes the predicted FEC FLR. So just to give you a quick outline of how this prediction is done. So the FIC histogram data we look at, and typically the data we'll be covering further in the form of slides, but I'll just give a quick overview. So we will have the FIC data, which is the number of code words with the specified symbol errors in the form of exponential decay curve. So that's what is being mentioned here. Okay, sorry. Okay, and then we apply a linear regression algorithm to it to transform the exponential curve into a linear curve. And then we apply linear regression to predict the values, and then we extrapolate from there and compute the predicted FLR. That's the like high level details. Just coming to the graphs. So this corresponds to the FEC errors that we see, number of symbol errors. So we saw in bin 0 there was like lot of like things falling under bin 0, and bin 1 had again higher number of things, but as it came to higher bins it was kind of nothing or very close to 0. So that's what it represents. And then now we are seeing the same graph in the logarithmic scale. The original one was in like normal scale. So in the logarithmic scale it will look like this. It looks more linear, and hence we use the linear regression algorithm to find the line of best fit. So that's what we do here. And then next comes the extrapolation steps based on the linear regression algorithm. So we are kind of extrapolating the new points. So the extrapolation kind of figures out what would be the CER, what would be the number of symbols with errors with 16 and above. So which is when, right, the FEC will not be able to correct for RS 544, 514. So it corrects up to 15. So anyway, that is all correctable. So when it starts spilling above, it cannot correct. So again, we convert back to normal scale from logarithmic scale to back to normal scale by applying the exponential function. Then it looks like this. So those are the ones we see here are the extrapolated points. So coming back to the formula for CER in a different way. So it's like the number of code words that have specific symbol errors ranging from 16 to 30, which correspond to the uncorrectable range but detectable. So they are detected but couldn't be corrected. So whatever code words which have that many number of symbol errors by total number of code words. So that's the kind of CER. So for predicted CER, we just limit ourselves to just use only up to 20, because usually the numbers are tapering down. So after 20 or something, right, it will be even lower. So it doesn't make that much of a difference trying to compute, extrapolate more values and try to include in our formula. So we just stop at 60. So it is just 5 or 6 values we are picking. So yeah, so this is the thing, and whatever we see here is just the extrapolated values from the previous graph. So that corresponds to the points which we have just figured out here. So once the predicted CER is available, computing the predicted FLR is exactly same as what we did for regular FLR. It's no different. So we now have a new column, FLR predicted, which will be a bit non-zero before itself. Like the FLR is 0 all the time unless the link has a real problem, but the predicted FLR shows non-zero values. And if it is beyond some FLR objective that is meant for specific links, then it kind of means some proactive action needs to be taken, like need to check what is happening kind of for the operator. Okay, so we also I would like to highlight, we are not talking about that in the presentation. So we also have this FEC pre-BER and FEC post-BER, which was done by Arista and contributed in the 2024-05 cycle. I think it was mentioned in the presentation also yesterday from Luhan. So this is also there, but yeah, in the interest of time, we decided not to cover those details in this presentation. So we'll talk also about telemetry. So all this data, FLR and everything is part of the rates table. Unfortunately, there doesn't seem to be a virtual path for rates table support in SONiC. So anyway, without virtual path, we can still always get the data by following the OID indirection in SONiC. That's always available. So that's what it looks like first. you have to guess the OID of the corresponding port object, and then get the, using the OID, get the other attributes, which also includes the FEC-FLR. So that's what it entails without using a virtual path. So we also had a virtual path support for the rates table itself, which helps us to avoid this indirection in the first place. Like, we don't need to kind of do 2-level lookups. It's just 1-level lookup. We just give the port name and we get the data directly here. So this is done. So just talking about the status. So we have FEC-FLR support in SONiC. HLD is already out for maybe a couple of months or something. We had HLD reviews in the L1 subgroup. So implementation is pretty much internally done. So we have to kind of start upstreaming the PRs. We are targeting 2025-11. The BR was targeted for 2025-05 and it was delivered. So we are targeting this for 2025-11 now. Okay. We also like to specifically thank the members of the Microsoft team, Prince, Cameron, and Navneet, for helping us with this project on multiple fronts, from requirements and sharing with us some of the scripts which perform the predicted FLR computation. And they helped quite a bit on multiple fronts. I would like to thank them, and also community and everybody who has come here and joined us in the presentation and be part of the SONiC community. Thanks.
Thank you. Any questions?
Hello. Hey, this is Bala from Nokia. Hey, thanks a lot. This is quite inquisitive session. I'd like to understand, currently we have a counterpole logic. I hope the new attributes will be rolled out in the PR. We will take a look. Currently the counterpole logic is existing. We have a default value. And you are superimposing with 122nd for computation. Are we planning to change that logic? Also, how we arrive to 2 minutes cycle for this predictability or FLR computation? Some logic like to know. Then third question is related to any daemon we introduced in SWSS for this, or are we using the current?
So I will take, I couldn't follow the second question. I'll ask about it. The first question is regarding the pole interval factor. Right now it is not configurable. For now we have made it, it should be a multiple, actually for the counters table there is a pole interval which is 1 second by default.
Yes.
So it has been made as a multiple of 120 of whatever is there. Okay. So we don't want, we have a PR which is coming up trying to make it further configurable. Okay. But it will be a multiple of the underlying pole factor, not an arbitrary multiple of that, because it has to align with the FEC stats which is fetched from the soil layer. So that is not done, but we have plans. It got discussed in the HLD, so we are going to make it configurable instead of fixed to 120. So that will be there. Okay.
The second one related, how did you arrive for the whole time for 2 minutes? Is there any logic behind how we have?
Nothing specific about it. We just thought it's a nicer interval, and based on the customer requirements, we went ahead with it. There is not maybe great logic, and one of the reasons to provide it configurable is customer can configure.
Okay. That's.
So you had third question. So you were asking about, is there some daemon or something? Most of this FLR computation is happening in the Lua script. We have a new, there is a port rates.lua. So now we are adding some port rate FLR.lua, something like that. One new script is getting added, which is doing all these computations.
Okay, so when you meant SWSS changes, you meant Lua.
Most of it is in, everything is in Lua.
Lua.
Okay. There are minor changes to just invoke the Lua script alone outside in C++ or some other place.
Okay. Great. Thanks a lot.
Thanks.
Hey, thank you. It was great. I had one question on how much would be the bandwidth loss when we kind of turn on this FEC. So is it like when you said 514 to 544, is it like 30 bits of 30 parity bits injected for every 544 bits?
No, I could see 544, 514.
Yeah.
Those are number of symbols.
Okay.
Each symbol is 10 bits.
Okay.
30 symbols are for parity.
Okay.
So you are basically 30 multiplied by 10, 300 bits
Yeah.
for parity.
300 bits per how many bits?
Per 514 symbols, which is message. So 514 multiplied by 10, which
Yeah.
is 5140
Yeah.
bits
so,
of the message.
So basically 30 symbols to every 544 symbols or 514 symbols, which is like 6% of bandwidth lost.
Correct.
Yeah.
Okay. Now, okay. So bandwidth question is answered. The second question that I had was, when you find a packet which is, let's say, corrupted and you are trying to kind of reassemble it or correct it, right? Is it done in the software?
No, this is all at a very low level in the hardware.
In the hardware
Yeah,
itself.
nothing to do with the software.
Okay. So, and then what is the kind of application where you would use something like this? Because, see, for TCP based application, the transport layer takes care of all of these even if the packet is lost. I'm just trying to understand, because you are losing 6% of the bandwidth.
So, right, again, I would just like to clarify, yeah, this is all part of IEEE standard.
Exactly.
So, above 100 gig and more, right, and even at lower levels, FEC is generally mandatory. Like, we cannot afford to run the connection without FEC. There is always going to be some small errors which is happening in the link, no matter how good the link is. All like service, at least some symbol one errors and all will be present. So that's why FEC is there in place. And about the bandwidth loss, yeah, the lower layers have been built to kind of oversubscribe or have the additional thing to support this. Like if we talk about 100 gig, it will be like on top of 100 gig something will be there, the real underlying bandwidth, so it will kind of really support. Yeah,
Oh,
this.
I get it. So you are doing this at L1 layer.
Yeah, this is all part of IEEE standard.
If you see the name of the presentation, it is L1 telemetry.
Yeah. Okay, got it. Yeah. Thank you.
Again, yeah, these are all like FEC and everything
Per
is
standard.
not done by us. Like it's all as standard.
Got it.
Computation of FEC FLR is what we did. Yeah.
Thank you.
It's kind of hypothetical. Hypothetical question. Especially the predictability, the column. I was just thinking, will it be a reset safe? Because if you do a flap, that is a magic number. We can still retain it so that the operator can have a view of what happened fast. Is it a reset safe?
Right now, we don't have...
Mostly counters are not reset safe. Especially I'm interested of that column, specific column.
So right now we don't have support for it, but there has been an ask in the HLD to kind of maintain the max value or something to until some explicit clear is given. So for example, the BER, I think recently it has been added in upstream, FEC BER max or something like that. So similarly, there is an ask for FEC FLR max, which tries to store the maximum FEC FLR scene. So we have not implemented it, but that's possibly on the cards. Yeah.
Okay, yeah, thank you.
So there are multiple parameters, right? This here on your left, Amit. So
Hi, this is Madhukiran from Marvel here. Here.
Can't see you. Can you raise your hand, please? Thank you. Yeah. Now I can see you.
Yeah. Okay. First of all, nice presentation. So I have one question on extending this to have a BER also separate column together, because I saw a column where FLR was there, which is showing non-zero value, and after that you had a column where some FLR showing zero value and the next column showing non-zero value. So if you try to put the BR also, which is actually coming out of PRBS 31 or something, which creates more stress. So can we predict the link quality in in some more details? What's your thought on that?
So you want to predict the BER also? That's the ask.
Yeah. So it will be all in one place. So Ethernet and the lower level PRBS pattern BER also, if it's in one place. So FLR and your FLR rate and BER also there means in a single shot you would have a more greater picture of a link quality is what my thought.
Maybe, yeah, that's something
It is, I mean,
we have not
output-
got that requirement, yeah, so we have not done it. But one thing about the BER is it is the kind of worst case BER, because we
Correct.
generally don't get the actual BER from the underlying SOI or the underlying layers. So we consider one symbol is errored, we consider all the bits in the symbol has got corrupted. So we compute BER as per that. But yes, we can technically maybe extend the logic to that as well. I need to think a bit. I have not thought about it.
Yeah, why? Because I don't see a PRBS implementation there in SONiC yet. So we have it on the lower level SDK. So if we bring it up to the SONiC level, right? So it will be a more extensive test than our FEC FLR. So in one snapshot, we would have a greater picture on the link quality. So let's say your FLR is 0 and your rate is non-zero, and the next column which has the BER, right, which will give a more picture like, okay, this link is also might go down in some days.
Yeah, sure. Yeah, that's something that we could do. Yeah, I think FEC FLR indirectly indicates that, but
Yeah.
that's a different metric though. Yeah,
Correct.
it can be done. Yeah.
So because underlining is the PRBS 31, which creates more stress than our normal Ethernet packet. So it will be more onto the link quality. That's it.
Okay.
Thank you.
I mean, to be honest, because this went in the direction of expecting us to implement FLR,
Okay.
I guess that is more prevalent, to be honest.
Okay.
But nonetheless, point taken, we'll see what can be done.
Thank you.
Okay, Amit here. This is a little bit more basic. So there are multiple metrics, right? There's prefect BER, postfect BER, and then FLR. So how do you use that to derive your decisions, right? Between these multiple parameters, are they correlated, or do you look at all of them and make some decisions? You look at one of them and make a decision. What is?
Here, yeah, everything is based on post-FEC data. So whatever we have computed, not pre-FEC, at least for the FLR part.
Yeah, but you're projecting data. What decisions can be made using the data trend, right? Between FEC versus FLR.
Okay, so if you ask me what exactly is done in the deployment and how do you take the decisions whether link is going up bad or not, no, I don't know directly about it. But it makes sense to me logically that if the bins are starting to fill up from 1, 2, 3, 4 to 15, over the period of time, it is a clear indication the link is going down.
Yeah, but you
Right.
get that indication from BER trend also, right?
Right, but the predictability that comes into picture from the prediction of the FLR is going to help more, certainly. Yeah.
So there are standard metrics for BER objectives and FLR objectives for each type of the link. So right, 10 power minus 13, 12, all of that. I don't know the exact numbers right now, but so having that kind of number allows operators to compare, am I meeting the FLR objective for this speed or that kind of link. So that's what it kind of brings to the table, instead of trying to, anyway the pattern can be observed without this data itself, kind of by looking at the FEC histogram. But if you want to have a more objective thing, whether I'm meeting the standards objective or whatever I want to have, that it becomes a more like single number that tells how things are doing.
Is there any way we can detect deterioration? I mean, maybe more from a practitioner's point of view, somebody who may be looking at that. Do you see these curves change and then use that to say, hey, this is deteriorating? So is that something you see in the field?
Yeah, that we have seen, So even actually the data that we showed in the presentation was one of from the real switches inside Arista.
But I see it as like one graph and you're trying to predict, if there are more errors, what happens. I didn't see like multiple graphs that the histogram changing over a period and say, hey,
Oh, that we have not, we have just captured for at a specific point in time based on whatever we have seen. But we do see some of the links going bad over time. The bins will start.
Is there any other insight somebody can share in terms of?
Exactly, if somebody has more insight from the deployment and observation perspective monitoring, that will really help.
You should.
Okay. Thank you so much. Go ahead. Go ahead.
So do you think it will make sense to also capture the prediction error over time? Or is the prediction done only on demand?
What do you mean by prediction error? You mean like the linear regression? Like
so we have predicted something, right?
Okay.
And whatever we have predicted now, there are or there may not be subsequent errors which match with whatever we had predicted. So do you think for somebody reading this data, having a historical trend of the error would give kind of a nuanced view of how much should I rely on that prediction or not?
There is no plan for that as of now, but one of the factors, right, that is again not done yet is exposing an accuracy column in the parentheses. There is an accuracy with which the linear regression works. Anyway, you don't get an exact line, right? So it's based on that we try to compute that. That is not yet done and not captured here also. But you are probably asking about, we predicted something, then you saw something.
Yes.
So is there something that can be done on that?
No, actually, generally this is telemetry data.
Yeah.
So it gets exported, and there is somebody who is collecting the data. That is where probably the intelligence can be kept
Potentially,
more.
I mean that can be done here, there as well. Yeah. Okay. Thank you.
One more question there.
To answer your thing, we have to do A/B testing. For that.
A/B testing.
Yeah.
Thank you.
We have to do the A/B testing.
Okay.
I was answering him, not you. So I think these effect parameters are being fetched from the NPU SERDIS, right? So nowadays, these effect is being supported by the transceivers by themselves, and it is recommended to use the effect within the transceivers. Also, the modern transceivers like ZR Plus and all, right, supports these effect parameters being that could be fetched through CMIS. So do you have you explored doing similar thing for those kind of optics as well, because that's handled totally by a different module, PMON, rather than SWSS.
Hey, can you please introduce yourself also?
My name is Jemston, is from Celestica.
Okay. So we have not gone into the deeper layer. So as we kind of started with the presentation, we kind of noticed all the data that we need to compute is already exported, like fetched from the SAI calls, and it was available readily in Countess DB. So it was kind of pretty much software work on top of what is available in Countess DB. We didn't kind of delve too much into how different paths are being taken to potentially get the data into Countess DB itself. Yeah.
Okay. Because when using the ZR class and all, right, it's a long range optics. So there the FEC actually plays a more important role rather than this short range.
Yeah.
That's why.
No, I mean, the thing that is implemented is on top of SAI pretty much, I would say. So how the lower layers bring up the data, whether it is from ZR optics or something else, it's going to be up to the...
Yeah, that's actually rather from a different module altogether. So just want to see that area is also as concentrated as well.
So unless you are saying that the data for FEC stats will not be in Countess DB, right? It shouldn't really matter from PMON or somewhere else it comes and sits. I don't know about the details, all the details.
Okay.
If it's going to be a bit different for that case, but I don't think so. Yeah, but if there is something, you can tell. We have the HLD PR already out. Yeah, so you can maybe comment there as well.
Okay. Sure. Thanks.
Maybe this may be topic for next year presentation for you, but maybe comparison of cost versus ROI analysis of LLR and this, right? Because yesterday we were talking about, how do you get the acknowledgement number, right? Instead of parity bits, you could do that. And how these two overlap, right?
Go together.
Trying to visualize,
sense.
right?
Yeah.
So it will be a good area to... I'm sure there are folks who have that deep knowledge somewhere the practitioners have.
Yeah.
The rest of us, that will really help us, I think. Right?
Sure. Thank you so much. One more question? Okay.
So are you planning on making the FEC monitoring and the error monitoring into your observability solutions like Cloud Vision,
Right now, I would say it should be done, but from the Arista's perspective, we are not thinking specifically from Cloud Vision perspective as such. There are other EOS side things from Arista, which we call as LFS, for example, link fault signaling, which does not directly this one, but monitoring, for example, the link in terms of CRC errors, in terms of runt errors, and based on that, if you want to take some actions like syslog or shutting down the link, etc., those can be done directly today. But this specific thing, integrating with Cloud Vision, I'm pretty sure eventually it will happen. Yeah. That's like telemetry data being exported to the software where it is monitoring the entire telemetry data and taking some decisions. That will happen. Yeah. All right. Thank you so much. Thank you so much.
Thanks a lot. Great session.